Hello and welcome to this quick review looking at how to construct redox equations from scratch. There's several approaches that I'll take you through during this clip. We'll look at constructing a half equation from known reactants and products for either a reduction or oxidation process. And then we'll look at combining two half equations to create a balanced overall redox equation. And we'll also look on how to balance for electrons, species and overall charge while we're doing these two processes. So in this worked example, it tells us that iron reacts with aqueous copper 2 ions to form iron 2 ions and copper metal. And it asks us to write the overall redox equation for this process. So you'll also put a red dot next to where it says constructing a half equation, because that's what we've got to start off by doing. So we know what the reactants and products are, so we need to write those out. So once we've established what the reactants and products are, we can decide what our half equations might start to look like. And obviously we need to try and think about what reactant turns into what product. So let's start with the iron. So iron's oxidation number increases from 0 in Fe metal to +2 in aqueous Fe2+ ions. So this means the iron has been oxidized in this process and therefore loses electrons. And if we do the same for copper, we can see that copper has been reduced. So now we can work out what the two half equations might look like. So because we know that the oxidation number increases by 2 in iron, that must mean it's lost 2 electrons. And because the oxidation number in copper is decreased by 2, it must mean that has gained 2 electrons. So now we've created the two half equations, we can look at how to combine them. So it's quite easy to see that you can balance the electrons by cancelling them out. Now what you do is you simply add together everything that's on the left and make the reactants, and everything on the right and make the products. So that gives us the overall redox equation. So this was a fairly simple worked example. Let's have a look at a slightly more complex one. So in this case we have to do the same thing, but there's a lot of other information that's there as well. So it mentions concentrated sulfuric acid. Don't feel you have to put H2SO4 into your equation. There's a reason for that, and that's because concentrated sulfuric acid in this particular role is a source of H+ ions. So I'm just going to pop down a reminder for you. Whenever an acid is mentioned either by name or perhaps in terms of acidic conditions, when we're talking about redox equations, this means that H+ ions are part of the reaction. And this also means that they'll convert to H2O as a product. So this is something to be aware of when you're constructing your half equations. So let's now clear a little bit of space and do the half equations for this particular example, just like we did before. So if we put the reactants and the products as listed in the question, you'll obviously see that the oxygens that are present in H2SO4 don't seem to be present in the H2S. So where have they gone? This is where the idea of H+ and H2O comes in, like we talked about a minute ago. So let's start with the oxidation. Hydrogen iodide is oxidized to iodine. So I've doubled the moles of HI because I need 2 iodine atoms per iodine molecule. And by applying oxidation numbers to iodine on the left and on the right, because I'm making elemental iodine, I've gone from -1 to 0. But this has happened twice because there's 2 moles of HI. So now I need to put in the electrons to justify this. So now this gives me my my oxidation process. Now you'll also notice that the hydrogens haven't gone anywhere. There's no hydrogen, it's not balanced for hydrogen yet. Although it might seem strange, it's actually okay to leave that for now, because you need to take care of the electrons first, then the other reactants and products can be slotted in around them to balance the species out. You can't do everything all at once when you've got a more complicated example. So applying the same idea to H2SO4, I can see that the question is telling me it's a reduction, So I've left some space to put this in on the left hand side to put in the electrons. So using oxidation numbers for sulfur, it's +6 in H2SO4 and -2 in H2S, tells me that there are 8 electrons gained in this reduction. Now, to balance those electrons, what I have to do is the oxidation has to occur 4 times and the reduction has to occur once. Now if we look at the reduction, it means we're now looking at species and we're also looking at charges. Because if you remember, I mentioned those a little bit earlier on, it's up on towards the top of the screen. We also have to focus on how to balance for electrons, species and overall charge. So in the reduction, there's a charge of -8 on the left because of the 8 electrons and 0 on the right. In the reduction, the equation is not balanced for oxygen. So both of these have to actually now be addressed. So using the supply of H+ ions from the acidic conditions to balance the charges, I put an H+, 8H+ on the left hand side. And to balance these 8H+, I put 4 H2Os on the right hand side. So now you can see what can be actually balanced out, or cancelled rather. So by getting rid of these, that allows us to produce an overall redox equation like that. Okay then, let's summarise what we've looked at so far. So half equations are multiplied to the lowest common multiple, so the electrons balance. And you can use H+ ions in acidic conditions to balance the electrons' charges out in either one of the half equations. And you can use water molecules on the product side to balance the H+ ions you've just used to balance the charges and the electrons. So we can also have a look at some handy tips to share with you, so that it might be a little bit quicker to do this in future. So to summarise, water molecules as products will always use up both H+ and O atoms. If H2O appears on both sides, cancel it down. And in addition, sometimes you also get redox reactions occurring in alkaline conditions, so OH- ions can perform a similar balancing or cancelling role as H+ can from acidic conditions. So we now have 2 examples for you to have a go at using the ideas we've talked about in the last 2 examples. So this is a 2-part question. And what you need to do is pause the clip and try these before playing again. I'll obviously take you through the answers, but see if you can do it yourself now. So first start by thinking about the reactants and the products. So looking at the first one, it says in acid conditions, so we need H+ as a reactant, which would obviously give us H2O as a product. So looking at the remainder of the reactants and the products they become, it's quite easy to work out what's what. So now we can do the half equations, the reduction and oxidation. So the oxidation is easy enough because silver just oxidizes to Ag+, and it loses 1 electron. Silver loses 1 electron to produce Ag+. Now what you've got to do is look at the reduction. So putting the reduction half equation in, you'll notice that I've left spaces for any balancing numbers. I don't know how many electrons I'm going to need, and I don't know how many H+ I'm going to need. And I'm just leaving state symbols as optional here. I've put them in because I happen to know that nitrogen 2 oxide is a gas, but unless you're asked for it in your exam questions, you don't have to put that in. So the first thing to do is to work out the oxidation number changes. So if you look at the fact that nitrogen is +5 in NO3- and +2 in NO, that means it must have gained 3 electrons. So now we know that we've got 3 electrons that are needed. We've also got to balance the charges. So on the right-hand side you have an overall charge. And on the left-hand side you have 4 minuses, NO3 minus and 3 electrons, and 1 plus. So you've got to work out how you're going to balance those charges out so that's 0 overall. So like we said earlier, you can use the H pluses to do that. So 4 H pluses will balance 4 negative charges, so the left-hand side is now also 0. So now you can use the water on the right-hand side to balance the H pluses that you've got on the left. So by doing this, it will automatically balance the oxygens for you on both sides. So now what you've got to do is multiply up the other half equation so the electrons balance. So now you can cancel the electrons. And you can combine the two sets of reactants and products. And this gives you the balanced redox equation overall. So what I'm going to do now is give you the balanced redox equation for the second one. Why not try and work through using the steps I've just used to see if you can do that one in the same way. So work your way through the same steps that we did in the first example to see if you can arrive at this final redox equation for the second example. It's good practice, as always, and once you've done that, why not go and find some other examples to try along a similar vein. So in the meantime, thanks for listening, and until next time, see you soon.